Today we're going to be tracing Prim's algorithm. Prim's algorithm uses a BFS, so it uses BFS to find the minimum spanning tree, the MST of a graph structure. Say we had this graph structure with node weights, or the edge weights 5, 3, 2, and 7. The minimum spanning tree would be 3, 2, 7, as it is the most cost-effective way to connect all edges to every node. So we have this sort of priority queue happening here, and this priority queue is going to keep track of what edges we should be evaluating next. So for example, if we had some starting node S, and the starting node S had 3 connections leaving, so 5, 3, and 2, we're going to have this priority queue that's going to list these, and we're going to know to evaluate 2 next. We're going to keep a distances table to know, should we keep this edge or drop it? Is this the best edge? Have we found a better edge? And we're going to keep a parents table to understand who is holding who. So now with that, we can start tracing. And one more thing. Prim's algorithm is meant for undirected graphs. So nothing directed, it's meant for undirected graphs. So nothing with arrows, no directions. So now let's evaluate this undirected graph. First we started with S being 0, and everything is going to be equaling infinity. We first evaluate S, as it's the first thing on our priority queue, and we're going to look out from S. We see that A is 2, so we put down 2. We see this connection 5 to C, so C is now 5. See this S connection to B, and B is now going to be 1. Now we're going to look back at our priority queue. Our priority queue here says pick 1, so we're looking out from B. We're B here, we're looking out from B. We see 3 to C. 3 is this new best edge to C, so the parent of C here is B. And now there's nothing really we can do, so the next thing we can evaluate, we look back at our priority queue, we see this A, so we look out from A, and we see this 2 connection going to E. So the new parent of E is going to be this A connection here. So E is now going to be 2, and now we see this 7 connection leading to D, so we put that down. Now that's all A can really see. So now we're going to look back at our sort of priority queue. Now we're going to look at E and evaluate from E. Now E is going to look out, this E right here, and it's going to see this 1 connecting to C. So C is now going to get 1. E is going to be the new parent of C. And it's going to look at this F here, and F is now going to have a new parent, so E is going to be the parent of F. F gets 1, and E is going to look out for D. It's going to see 3 to D, and D is going to get this 3. And now G, it sees this G connection. G is going to get 8. Now that's all the things E can see that we haven't visited. We can't go back because we have this sort of BFS structure. We've already visited A. We can't go back to A. So now we're going through, and we look at our priority queue again. Let's take this C. We've had C for a while. And now let's look out from C. There's nothing new. Well, there's this new connection from F, but it's not really going to add anything. So we're looking, and that's sort of it for C. And now we look back at our sort of priority queue. We see F. Looking out from F, we see this new connection 4. So this 4 connection, looking at G, then 4. So F is the new parent of G. And now we're going to evaluate G. Nope, there's a 3 here, so we're going to evaluate D. So looking from D, we see this 1. And now the parent of G is going to be D. And now that's G. G has this 1 connection. We evaluate this. There's nothing new that we haven't looked at. So that is the end of the sort of trace. Now, did we actually get the MST? Let's draw this out. So we start with S. We got this 2 connection. We got this B connection here, C, this 1 from C was this E here, so E was the parent of C. That's why we need the parents table. And then you see C, so we just got C. Let's look at D. D had this 3. D had this 3 here. And E had this 2. This was this 2 connection coming from A. And now this F, this was this connection coming from E. And then G, this 1 connection. This 1 connection was coming from D. This looks to be the MST. So this is a Prim's algorithm implementation in Python. And before we sort of look at this, it should be noted that we have this sort of tuple arrangement happening here. So tuple is a pair of numbers, so a pair of x and y numbers. And what we're going to be using tuples here to sort of arrange the weights. We have the weights in the first slot, so the 0 index, and the actual node in the 1 index. So it's kind of like a shorthand quick array. We're going to use this to our advantage to sort of keep this priority queue. So again, we have the distances table that we're going to keep track of. We set everything to infinity. We need the parents to keep tracking of who's holding who, and any visited table, so basic parts of BFS. And then instead of in BFS we had a queue, now we're going to manage this with a priority queue, so a min-heap. We have here, see, this is an example of how we're using this tuple, as we start S out with 0, and to make sure and sort of keep track of, okay, we want to order these weights, but when we pop these off the min-heap, who do they belong to? So that's the main reason why we have these in tuples here. So the distances table is going to tell us what are the best distances that we have, and we first set S to 0. So this one is for the priority queue, and this one is for the distances table. Then we're going to run regular BFS right here, run regular BFS, and then we get to this. We get to sort of this statement right here. So all this here is just BFS, and this is the special, this statement is the special one. So now when we're looking at sort of the outgoing neighbors of, what do we have, node, so this is node. We're looking at the outgoing neighbors, so C are these edges, so these nodes that we're reaching out to, and we're looking at the edges. So when we look at the edge weight of C, so we look at the C right here, the edge weight. Is this edge weight less than what we have in our table? So if we find something less than, we're going to take this path. And we're going to set the new parent to this node, the one that discovered it. And that should be the basic sort of rundown of how this algorithm is working. But what is the runtime of this? So to solve this runtime, let's look at this portion right here. If we were to only look at this as if we were doing BFS, BFS would have a runtime of n plus m. But look here, on this line right here, this queue insert, remember that that's our priority queue. And when we rebalance a priority queue, so when we're inserting an item, that's going to be log n. So if we're doing that every time we're doing our BFS, that's going to amount to big O of n plus m times log n. This is going to give us n log n plus m log n. But recall, so we're going to want the bigger portion of this plus sign. So this side or this side? Well, it turns out, recall that m is less than or equal to n squared. This is if all nodes are connected to each other. So we're going to get n squared. So in reality, this portion is bigger than this portion. So in the end, our runtime is big O of m log n. And that is the runtime of the Prim's algorithm, m log n. So what if instead we used a hash table? Recall that our two main functions that we did with our priority queue was extract and insert. And what we were doing with the priority queue is storing our weights. So what if we stored our weights in a hash table? Well, we'd have to go through all n to find the next suitable solution. So for our extract here is going to be big O of n, because we'd have to go through our entire hash table. And then, what about insert? So insert. So what if our hash table, we called our hash table H? Well, to update an element in a hash table, all we have to do is index it. So that's just going to be big O of 1. And let's look at our algorithm again. And if we were to look at our BFS here, this BFS, when we get or pop elements off in BFS, we're only visiting a node each time. So this is going to be n here. And then to extract, so for every n, we're going to extract, so it's going to be n, a big O of n times n, and then the rest of our BFS, that's going to be m. And that's going to turn out to n squared plus m. And we know again that m is less than or equal to n squared. But often in practices, it's not going to be n squared. So really, we can just take this n squared. So the runtime of the hash table, algorithm is going to be big O of n squared. But why do we care about this? Why do we care about the hash table implementation? Well, let's look at our original implementation with the min-heap. That was big O of m log n. But what if m, so recall, what if m, so m was less than or equal to n squared, what if m was n squared? So that would mean n squared log n. But that's larger than n squared by itself. So why would we ever use a min-heap? Well, in reality, m is not going to be larger. M is not going to be larger than n. That's just not going to be the case. You know, when we look at trees, tree structures, so here, a tree, m here is usually n minus 1 for a tree. So in practice, m is not going to be larger. So in practice, we're going to get m is less than or equal to n, most of the time. So in those cases, when m is less than or equal to n, we're going to pick the min-heap solution. But when m is larger than n, we want to pick this hash table solution. But in most cases, we're not going to have that many m connections, so we can be safe to assume and pick the min-heap solution. But if m is larger, again, we are going to pick the hash table solution. And that is it for this video. If you enjoyed it, don't forget to like and subscribe. If you're looking for the code implementation of Prims, it is linked in the description below, along with an open source free textbook for anybody to contribute to. And with that, thank you.